Thank you very much for inviting me. It's a pleasure to be here. Can everybody hear me all right in the back? It's okay? Good. All right. I'm going to talk about Sequoia today, and you saw me fiddling with names just before the talk began. I decided not to try to list all the people who have been involved, so it's just my name up there, but actually a lot of other people have been involved in this project, and I'll mention Pat Hennerhan and Bill Daly as other faculty, and Kayvon Fatahilian, who was the primary PhD student, but a lot of other PhD students actually worked on this. So what's the idea behind this project? The basic idea is stream programming for machines with deep memory hierarchies. And if you don't know what stream programming is, I'll give it a definition in a minute. So this is just one way of motivating it. But the basic idea is that programming languages tell you a lie about the structure of the machine. And this is a very useful lie, or has been historically. The view is that every memory reference that you make costs the same. There's no way as a programmer to tell, in most programming languages, whether there are at least some machines where we'd really like to expose the structure of memory because the programmer wants to write programs, programmers want to write programs that take advantage of it. And just cutting straight to the end of the talk, the implementation runs well on lots of machines with complicated memory hierarchies. And these are some of the ones that we'll talk about later on. So coming back to the motivation, the key challenge in our view in high-performance programming is not computation. So it's usually pretty easy to find parallelism and to express parallelism. It's actually the movement of the data, so getting the data to where it needs to be. And dealing with latency and bandwidth constraints. So what is streaming? So essentially, and this is very much a Stanford notion, but streaming involves structuring algorithms, as Ree was on the slide, collections of independent and especially locality cognizant computations with well-defined working sets. So what does that mean? That means that you have a computation, you know what data it's going to work on in advance, and that you're able to localize that data to some part of the machine and do all the work there. So you're not randomly grabbing stuff from all over memory. You actually move the stuff to where you want it to be, and then you work on it right in that place. And streaming languages and streaming computations have this structure. So, and we'll talk about the streaming work that's been done before in a few minutes, but I just wanted to observe at this point that this kind of structuring can be done at any scale. So compilers do this to try to keep temporaries in registers. So you try to pull stuff into the registers and you try to leave them there as long as possible. People do this for cache and scratchpad blocking. You try to access, size your arrays or whatever it is so they will all fit in the cache and they will stay resident in the cache for the duration of your algorithm. Message passing on a cluster, you try to keep the data local to the nodes on the cluster and not move stuff around between the cluster nodes as much as possible. Out of core algorithms, you have stuff that's way out resident on disk. You bring in a page or whatever, and then you work on it as much as possible off the disk in the main memory before you ship it back out. All right, so people do write algorithms that express this kind of structuring at lots of scales, and Sequoia is about bringing this up into the language and making it explicit so that you actually have language support for programming these style of algorithms. Okay. All right, so the goal is to develop hierarchy or to facilitate the development of hierarchy-aware programs. And that's for efficiency. So by being hierarchy-aware, we actually have a notion of locality in the language that allows us to write efficient code. But we also want to remain portable. So there has to be some degree of abstraction. We don't want to say, we have 7 memories, and this one's a 1K, and that one's a megabyte or whatever. We want it to be more abstract than that. And another constraint, being a compiler person and having grown up in the programming language and compiler community, I know how fragile these things are, and I have a love-hate relationship with compilers. On the one hand, I love doing research on them. On the other hand, I know that it takes an incredibly long time to get new compiler technology fully developed and deployed. So I think as a starting point, we need constructs that are going to work reasonably well without really heroic magic compiler technology. And you'll see what I mean by that. That doesn't mean the compiler doesn't have a role. And in fact, our compiler actually does do a lot of optimization. But the basic structuring devices are things that can be implemented in a relatively straightforward fashion. Okay, and what are these things going to do? We're going to place data and computation in the machine and also have explicit parallelism and communication. And one more thing I'll just point out now. It's a little bit of a detail, but I will come back to this again. We're going to emphasize large bulk transfers. So rather than individual memory references, we're going to emphasize moving big blocks of data around because that's what's efficient to support in modern architectures. All right, so a little bit of related work. Okay, so is that clock right? So I can time myself off of that clock? Good, all right. So where do you see people exposing the memory hierarchy or locality in programming languages currently? Well, so you see this in the high-performance languages, and primarily in what are called the PGAS or partition global address space languages. So these have a notion of data that's local to a thread and then global to the entire computation. So they have 2 levels, and example languages there are UPC and Titanium. There's a class of languages that have domain distributions, which talk about mapping array elements to locations in the machine. And this is also the PGAS languages, but it's also some earlier languages. And then this has been adopted by the next generation of languages. The most recent languages in this class are X10, Fortress, and Chapel. And these are really languages that, to a first approximation, were designed for programming clusters, where you cared about local memory on the cluster, and that was treated as sort of a normal sequential program, and then the other stuff. So that you either had stuff that was local or you had stuff that was far away. Okay, so 2 levels of memory hierarchy are made explicit in the language. All right. So then there are the streaming languages, which really make a distinction between on-chip versus off-chip. So you have a notion of a kernel, which is working on some data, which is on chip, and then there are usually pipes that are connected to the outside world. That's the stuff that's off chip, and stuff gets pushed in through the pipe, loaded onto the chip. The kernel does its thing, and then stuff gets shipped out off chip. So once again, it's a 2-level paradigm. When you're programming, you're explicitly aware of stuff that's local to the chip and stuff that's out in someplace off the chip. All right, and just to point out, there's a host of a series of really predecessors to Sequoia that use this stream programming paradigm. GPU shading languages look like this, and CUDA also has this flavor. All right. And the thing about these languages, they tend to be architecture specific. Okay. And generally, they only represent 2 levels. The exception being CUDA, which actually has 3 levels. Okay. So, these languages here, which are really CUDA predecessors, were again just 2-level languages. And then there are some theoretical models, things like cache oblivious algorithms, if you've heard of that, and space-limited procedures. And the only point to make about those is that those are programming methodologies and not programming environments. So they're not actual programming languages. Okay, so now let's talk about actually what these programs would look like in Sequoia. And I'm not actually showing any Sequoia code just yet, but I'll just talk about how people program locality-aware algorithms in general. And I apologize, but I'm going to trot out just the most tired warhorse in this area, which is matrix multiply. It's good because it illustrates the ideas and it fits on one slide, but you can actually write more programs than just matrix multiply in this or in any of these languages. So anyway, so here's a naive matrix multiply algorithm, just written in a conventional syntax, conventional language. And I'll depict what's going on more graphically. Like this, I'll say, I'll show you the size of the matrix multiplication and the three matrices with blocks suggesting their sizes. So the A and B matrices are being read, and the C matrix is being written. Okay. Now, if I want to block this for locality, if I want to write a program that's going to be memory hierarchy aware, and I want to do this in an existing language, what will I do? Well, I'll write a matrix multiply that recursively does a divide and conquer strategy and performs a bunch of smaller matrix multiplications. So I would break up the problem into problems of my leaf size, whatever it is, and I would do a whole bunch of those. So if I had 256 by 256 matrix multiplication, I might break that up into 512 32 by 32 matrix multiplications. Okay? And if I have a really big matrix multiply, I might do this recursively. I have a lot of the medium-sized matrix multiplies, each of which would be decomposed into a lot of the very small matrix multiplies. Okay? And so these are the kinds of algorithms that are efficient on hierarchical memory machines. They're essentially divide and conquer algorithms. Okay? So if you can write your program in this style, it's going to exhibit good locality because you will break up the problem in some way, and then you will localize the data in a smaller, faster part of the machine where it will stay while you do a whole bunch of other work, and recursively, possibly breaking it up into smaller problems. All right, so now let's switch gears. That's how people write locality-aware programs now. And now I just want to show a correspondence or suggest a correspondence with the structure of machines. So just like these divide and conquer algorithms can be viewed as trees, where you have big problems at the root that fit into large, slow memories, being recursively broken up, and at each level, the subproblems fit into smaller memories that are faster and closer to the processors. We could also view the machines as trees of memories. So a dual-core PC might mean two processing units with their small amount of local storage attached to a main memory. Okay? And if I want to zoom in and do a more a finer grain model of this machine, it would have a couple of caches in there, one of which is shared and one of which is private to each of those computational units. So I get a tree that looks like this. If I have a cluster of PCs, then I can represent the network as a level of the memory hierarchy. And let me come back to that in just a moment. Clearly, each element of the cluster has its own memory hierarchy consisting of a series of caches. And those nodes might even be dual-core or multi-core machines like on the left. So I could replace each of these simple subtrees with a more complicated one. The aggregate level there, this is something we need to do to model clusters in Sequoia. We treat a cluster level there as an aggregate of all the local memories of the individual machines. So it's what we call a virtual level, meaning that there's no physical memory. There's no single physical memory that actually corresponds to that level. It's the union of all the child memories underneath it. Okay? And so this corresponds exactly to the notion of local and global in the PGAS languages. So the local level is the node memory, and the global level is the cluster, because that might involve communication across the network, which is a lot slower, although you have a much larger total memory to work with. Going on, so IBM's cell blades would look like this. They have an actual physical main memory and then a whole bunch of accelerators attached to it, 8 accelerators attached to it. A dual cell blade has 2 of the accelerators attached to one power chip. Okay. A system with a GPU looks something like this, where you have the main CPU memory, the GPU's device memory, and then a whole lot of children. So just many, many, many children, hundreds of children potentially, each with its own very small local memory. And then finally, a cluster of dual cell blades. So this is the architecture of the Roadrunner machine at Los Alamos, which until very recently was the #1 supercomputer in the world. So it consists of a cluster of conventional CPUs, actually the Opterons in this case, and each of those is attached to dual cell blades. All right, So that was to convince you, that little tour was to convince you by suggestion and analogy that we can model machines as hierarchy, as trees of memories. Okay, and it's a relatively simple abstraction, but I'm going to argue this is a useful abstraction. So the programmer is just going to think of the machine as a tree of memories. And now we're going to write programs that are going to get mapped onto those trees of memories. And what do these programs look like? So in Sequoia, we have special functions called tasks that are the building blocks of the language. And so every language has to introduce its own special nomenclature, and ours is the task keyword. So these are just functions, okay? And here, for example, is the matrix multiply leaf. So a task that we're not going to break up into smaller tasks. It's a leaf task written in Sequoia. And for the moment, let's ignore the special new keywords on the argument on the formal arguments. Okay. Now, task arguments and the temporaries define a working set. Okay. So the arguments to a task define the data the task is going to work on. So the first rule about tasks is they have no external references at all. So they can't refer to global memory. You can't have global variables referenced in a task. No pointers to external objects in a task. Okay? And so a task lives in a closed world. A task plus its input arguments form a unit of computation. All right? So if a PGAS like titanium or UPC, is a global address space language, Sequoia is a local address space language. You only have local address spaces which are isolated from each other. So every task is isolated from every other task. And so in this case, it's just the three matrices that form the working set to a call to matmul leaf. All right? And the reason for this restriction is that that's how we're going to get locality, how we're going to get a handle on where this computation is going to run. Because the task working set is going to be resident at a single location in the abstract machine tree. So now I'm switching from the concrete trees I showed you before to some abstract tree where I just think I just have a bunch of memories, okay, arranged in some tree shape. Every task instance is going to be resident at a single location in the abstract machine tree. All right, and it's going to execute there. So the programmer's model is all the references in this task, when it executes, are going to be local references to the current, to the level of the memory hierarchy where the task executes. Now, those local references might be expensive if it's near the root, but as we go to the leaves, they will be, the smaller subtasks will be faster. All right, then we have hierarchies of tasks. So in a task hierarchy, we're going to now implement the divide and conquer strategy for matrix multiply. We're going to recursively call matrix multiply on submatrices of some size. Okay, and I'll come back to how we determine the size in just a moment. Okay. But notice here that I have two variants now. I have the matrix multiply inner. This is the inductive case where I'll be decomposing into smaller problems. And I have my base case, the matrix multiply leaf. When I get the problem gets to be small enough, I just have a direct implementation of matrix multiply. All right, now, these tunables. This is a new construct that's added in Sequoia. So a tunable is like a compile time constant. This is something that's going to be filled in by the compiler at the time that you actually compile for a concrete machine hierarchy. So you have your abstract hierarchy, the tunables are left open. But when you actually pick a particular machine with particular memory sizes and a particular number of levels, we're going to have to pick the sizes of the matrices, and they'll be chosen to fit at that level. Okay, so we'll fill in P, Q, and R, which are going to be, and we'll see the code for it in a second. Those are going to be determining the block sizes when we know exactly what machine we're compiling for. All right, and so here's what the code looks like. We have parallel map, and then a sequential accumulation for the updates to the C array. And then, let me see if I have my electric pointer. And then, in the bottom in the inner call there, we have a recursive call to matrix multiplication. All right, do I have it? No. All right, apologize for that. Is there a laser pointer down here? Or a physical pointer? Doesn't matter. I can point. All right, so if you see that call there to matmul in the middle, just notice that it doesn't have attached to it either an inner or a leaf qualification. All right? We don't know whether we're going to call the recursive case or the base case until we know what physical machine we're talking about. We need to know the number of levels to know whether any particular recursive call will be to the inner or the leaf variant, as we say. Okay, so there it is. All right. So the call graph then looks something like this, where we have a where we're going to call depending on the size of the machine, the number of levels in the machine, we'll recursively call the inner matrix multiply some number of times, and then we'll bottom out in the leaf. And what does this look like? So the calling task, okay, is going to be located at some level x. All right, and this is an instance of matmul inner, and let's say that this is near the bottom of the hierarchy, so we're calling the leaf task, okay, located at level y. All right, and it's going to be picking out smaller matrices A, B, and C. These matrices get worked on down here at the leaf level. All right, and now I can explain the in, and in-out keywords on the arguments. So task arguments will have these qualifications, in, out, or in-out on their arguments. And this is actually saying whether data is copied in, copied out, or copied in both directions. All right? So the in parameters are copied down, copied into the, thank you very much. I appreciate it. Thank you very much. And I apologize for being disorganized, not having it. So in parameters are copied down, okay? And out parameters are copied out on termination of the task. Okay, so in fact, the parameter passing semantics of tasks is call by value result. All right, so it's copy in, copy out semantics. And this is actually a well-known and long-standing, but not very popular parameter passing semantics. I think it kind of went out of fashion with Fortran 20 or 30 years ago. But actually, in these machines, you actually literally do the copies. Okay, you actually do move the data from here to there to do the work. So this is the parameter passing semantics that makes sense. And it has some significant advantages in terms of the compiler then knowing where the data is and what's aliased and what's not. So this actually, it helps with isolation. You're actually doing copies and not passing references. Okay, so the parallel map here, just to point this out, it just says that we're going to do these iterations of this inner loop all in parallel. Okay, and notice the tunables there. How many iterations we're doing is going to depend on the size of the matrices. All right, and the size of the matrices and the tunables. Okay, and because we have a task hierarchy where it's task and call subtask, we actually get nested parallelism. All right, so there's parallelism at this level, but there will be parallelism at every level in all the recursive calls to this particular function. Now, Sequoia is really not particularly about C++, which is the syntax that we're using here, or about fast sequential code. All right, it's really what it is about the communication of arguments and the structure of the computation. And so we don't care. We're not proud. We're not too proud to use fast leaf procedures. So if there's a vendor supplied, for example, leaf task, we'll just use that. And so this allows you to call out to hand or well-optimized sequential code on at the leaf level. And what we do is structure the movement of data at the higher levels of the computation.
I have a question.
Yes, and I should say, people can ask questions at any time. Go ahead.
Did you tell us where the source of information for the tunables comes from?
No, not yet. I'm leaving that ambiguous for the moment. I will tell you. Okay, and the answer, there's not just one answer, but we'll see a couple of different answers as we go along. All right? The important thing right now about the tunables is they need to be chosen differently for each machine. So it's something machine-specific, and we're trying to keep machine-specific machine-specific stuff out of the source programs. So The source programming language is designed so that you don't say anything about how big the memories are or how many levels there are when you write the program. But then to go to a concrete machine, you need to say. Okay, and we'll see how that works in a minute. All right, so what do tasks do? They provide a single abstraction for isolation and parallelism. They provide a unit of work, and the isolation is very important. So tasks are not threads. Tasks have no way to communicate with other tasks, and so that means that this simplifies scheduling dramatically. There's explicit communication. So actually, one thing I should point out right here, that's a strength of this particular way of organizing things that I think is so obvious that it's easy to overlook, is that the communication is really expressed. Where did it go? It's on this slide. The communication, all the communication is really expressed in these task calls. Okay, so this translates into movement of data in the machine. All right? But the particular protocol for moving data is left open. Okay? Whether we're going to use MPI to move this across a cluster or DMAs to move it between from the main memory to the cell's processor memory, or just memory references in a cache-based architecture, the actual mechanism for moving the data is left open until we bind it to a particular machine. This makes the programs much more portable. So if you look at what people do in high-performance computing today, if you look inside their programs, 80% of the code, 90% of the code is application or architecture-specific stuff for moving the data around, all the MPI code. There's a ton of MPI code, and then there's a little bit of actual physics or whatever it is that they're doing. And so this results in a big savings, and in terms of the amount of code you have to write, and gets a lot of, it makes the code much more portable. All right, so moving along. Okay, so now we're going to have, and these tasks are going to get mapped onto the memory hierarchy. I haven't told you how that happens yet, but I'll tell you in just a minute. And they're parameterized in various ways for portability. Parameterized by tunables, parameterized by the particular communication protocols, and those are actually the two primary things. All right, so now compilation. So compilation works on these hierarchical programs, and we actually do a lot of standard optimizations. Okay, and then by standard I mean all the stuff that you would learn in an introductory compiler course. But because we have this hierarchy, we can actually do these optimizations at all levels of the hierarchy. And this actually turns out to give us a lot of leverage. So let me give you an example. Interlevel copy elimination. So here is a case where I have some data so that's living down at a given level of the memory hierarchy. It gets copied back up to the parent level. This could be like an out parameter. These are the results of one task going back up. But then there's another task call which takes that as an argument, so it gets copied straight back down. All right? Well, compiler can look at this flow graph and say, I know a better way to do that. I'll just leave the data down here between the task calls. Okay, so now we just have an interlevel copy, and perhaps we can eliminate that copy as well. Okay, we can do another level. So this is just what you normally do when you do copy elimination on register-to-register moves. I write something out. I write a word out to memory. I load it back in. I don't have to do that. I can just leave it in the register. Right, but now these copies might be huge blocks of data. This might be millions of instructions, not a single instruction. All right, so by having this hierarchical setup, you get these optimizations at all scales. All right, and this it turns out to be very, as you can imagine, with all the explicit copies, this turns implied by the semantics. This turns out to be a very important optimization to do. Here's just another example. If I copy something twice down to a level, I only have to copy it once. Okay. So if a constant, for example, I have a bunch of task calls that all take the same constant first argument. And so I don't need to repeatedly move the data down. I can move it down for the first task call and just leave it there for all subsequent task calls. All right. Now, another example of it being able to apply standard optimizations at all scales. So software pipelining is a very common instruction level optimization where you're basically trying to overlap iterations of a loop. All right, so you're trying, if you have a loop that says, takes 4 or 5 instructions, but they're dependent on each other, and so there are big gaps in between them. So you move instructions from subsequent iterations up and overlap them with the first iteration. And if you do this in the right way, you can develop a closed form that allows you to do 3 or 4 iterations or 5 iterations or whatever at a time. Okay, well, so what's the analogy with tasks? So typically, because tasks are isolated, it's very common to write programs where you'll have many more tasks than processors. So every processor will do multiple tasks. Okay, you may have 1,000 tasks and 10 processors, and so each task each processor is going to do 100 tasks. And so one very common thing to do is to overlap communication and computation. I could be computing one task, and at the same time, I could be writing back the results from the previous task that I computed to the parent, and I can be prefetching the data for the next task that I'm going to execute, okay, after I'm done with this one. Okay? Well, this is just software pipelining with 2 resources. I have compute and I have communication. All right, I'm trying to make the best utilization of those. So I'm overlapping multiple subtasks at once. Okay? And so, but now I can do this at any scale. I can do this at any level of the memory hierarchy. I can get this overlap of communication and computation going and make full use of the machine's bandwidth to to keep everything in the machine as busy as possible. All right. Let me tell you a little bit about our runtime system. So we're moving down through the levels here. Now we're done with the compilation. We're going to talk about the runtime. So the runtime system provides a uniform scheme for describing these memory hierarchies. So the basic problem is going to be that we want to compile for all these different machines. We want to be portable across lots of different kinds of hardware. And that's going to be a very tall order if the compiler has to know all the details and actually generate separate, distinct code for all these different kinds of machines. So we're going to move a lot of that work into a common runtime system or a common runtime interface. So actually what the compiler does is it generates code for a runtime interface, for an abstract interface. And this provides a level of independence for the compiler that if you can implement that interface for any piece of hardware, then the compiler automatically targets that new piece of hardware. All right. So what does this runtime look like? Well, here's 2 levels of the machine hierarchy, adjacent levels. Okay, and the runtime system sits between 2 levels. All right, and it provides services both to the parent and to all the children. So essentially, the parent can make calls to do things at the child level, and the children can make calls to the parent, so there are entry points at the bottom of the runtime and entry points at the top of the runtime. And so this API consists of 14 entry points. It's basically different ways of moving data around. So the parent can allocate space in the child. We can set up we can initialize a runtime. The children can synchronize with a barrier. And then there's ways to move data. Either move data from a child to a parent or to move data from a parent to a child. And so this just simplifies the implementation because the compiler now generates code for one MPI and not many different machines. Each of these runtimes is isolated from all others, so there's literally a runtime for each pair of levels in the hierarchy, for each adjacent pair of levels in the hierarchy. And because they're isolated, that means that we can compose these runtimes. So you write a runtime for one level, okay, and then if you build some ad hoc machine that puts together components in ways we hadn't conceived of before, we can take the runtimes for each of those pieces and glue them and just stick them together, and that's a runtime for that aggregate machine. All right? So you'll see in the experiments, we are able to build all kinds of odd machines out of components left lying around in the lab and then just run on them and see what we get. All right. Tuning. How am I doing on time? Okay. So we've done some work on an AutoTuner for this system, and there's lots of parameters that could be tuned. So obviously the tunables are one parameters that can be tuned, and because those are used to abstract away from things like memory sizes. And the tuning framework is there to set these parameters. All right? So the tuning is done when you have a program and you have a definite machine that you're compiling for, and you want to set the machine-specific parameters. So this is answering your question about how how these parameters get set. And one way of looking at this is that the programmer in Sequoia gets to define the search space of the AutoTuner. So the things that are tunables, the programmer is explicitly saying, I'm going to defer that. I'm going to let something else figure that out for me. And if it's too hard or if it's too important, then I can take it back and make it a non-tunable and set it myself. All right? Or I can just leave it to some other automatic system to do. And our experience has been that the AutoTuner is really a big win. Okay, so it's never been worse than hand tuning, and it's of course a lot easier to do than picking the parameters by hand. And it's generally better and noticeably better in experiments. So a little bit of reality here. So the AutoTuner this is all a research project, but the AutoTuner is even more researchy than some of the rest of it. So it's not in our mainline compiler that we actually use every day. And so the way we actually set the tunables when we're writing programs ourselves or for other people is that we have a separate thing called a mapping file, which basically describes the settings of the tunables. So for each machine, we have a separate file where you can fill in the missing pieces, and then that just gets mixed in by the compiler along with a machine description file, and that's how the compilation works. So you can set the tunables either by hand, or you can set them with the AutoTuner, and the AutoTuner just isn't up to it isn't engineered yet to be part of the main line of the compilation process. All right. Now, why does the AutoTuner work well? How is it able to beat hand tuning? Well, one reason is that it just it's a lot more patient than programmers and is willing to sit there and try lots of possibilities. And most programmers get pretty tired of that, especially if they get good enough performance after a few tries. But another reason is that a lot of the machines we're compiling for, the memory is really software managed. All right, so we do compile for cache-based machines. All right, software managed, I should say, is code for no cache. All right, that's code speak for it doesn't have a cache in it. But it turns out that caches are really not all good. And if you're not somebody who's into performance-oriented programming, you probably don't appreciate this. But caches are actually really bad. Caches are good for better performance, but they're not really good for the best performance, because caches lead to all kinds of irregularities because of conflicts in the caches. And if you're doing software managed memory, you don't have that problem. And here's a picture of the auto-tuning space for a very simple application, two-dimensional convolution, on the cell processor, which has software managed memory. And the important thing about this space, why am I showing you this thing? Well, I'm just going to tell you, this is a smooth search space. Okay, so there are bumps in it here and there, and so what we're seeing here is the performance for every possible exhaustive setting of the two tunable parameters. Okay, and there's only two because it's hard to visualize anything, and we need a third dimension for time, and so this is what you can show in a convenient plot. But this is actually quite a smooth search space. And so if I wind up anywhere, if I just do a simple hill climbing algorithm starting pretty much anywhere in this space, I'm going to wind up at one of these high points over here, and they're all pretty good. Okay, maybe I won't get the best one, which might be this one right here, but if I wind up over here, I'm not going to be upset. All right. If this was a cache-based machine, the peaks and valleys would be a lot more jagged. All right, and so one reason that auto-tuning works well in this kind of a model is because the search spaces tend to be smooth. All right, when we're not dealing with hardware-managed memory. Just a couple of words about how the AutoTuner works. It's pretty straightforward. Because a well-designed Sequoia program should spend most of its time in the leaf tasks. If you want to be fast, we tune the parameters in the leaf tasks first. And then using those settings, we tune each of the higher levels recursively. Okay, so we tune the leaves, and we use that to constrain the tuning at the next higher level, and so on. All right, so we break up the tunables and set them hierarchically in that way.
Could you give an example of what you mean by tune the leaves? Would you try some bounded PQ and R to see?
Yeah, so we would just try all possibilities of PQ and R, all right, over some range. Okay, if it doesn't fit, if the program crashes, that wasn't a very good choice. So pick another one. Okay, and just keep at the moment at least, just do exhaustive search until you find the best set of tunables for a leaf task. Okay, the maximum data that you can fit that runs the fastest. All right, and then recursively, now using those, now assuming that those are the size problems you're going to do with the leaf task, tune the next level up. Okay, and so on. Yeah.
Probably related to this question, are you doing different profiling runs or?
Yes. These are in profiling runs. So you had to supply some sample data, you have to supply some typical data, and then you push a button, and actually, because it's not in production mode, you have to hold its hand and and write a script and stuff. And then it runs, and it just repeatedly runs over it takes that sample data and just tries out lots of different versions. And I'll say how it does the search in a second, but intuitively, it just searches over all the possible combinations of tunables for that task until it picks the best one. Okay? Other questions? All right. Then what about within a level? So within one level, we do what's called a pyramid search. And this is essentially just a greedy search on a multi-resolution grid. Because we're assuming we have a relatively smooth search space, we start out with a very coarse grid. We take big jumps and try tunables, sets of tunables that are relatively far apart. When we find a local maximum there, we refine the grid and search locally, looking for it, see if we can improve things. And if we still haven't found, and then we try even finer grids until we find a local maximum. Okay, and this works because we're assuming the search space is relatively smooth, and so we can just do simple hill climbing. We can take big steps initially, and when we reach a local maximum, according to that coarse analysis of the search space, then we can just refine and do a more local search. But this, this gives relatively quick convergence, is the point. All right?
It seemed to me, though, that anything can be a tunable, right?
Yes.
So then this assumption may not necessarily...
That's correct. That's correct. Yep. Yep. And I question, that is right. That is absolutely right. So tunables were originally intended to be for primarily the blocking sizes. Okay, in which case this assumption would hold. And as we went along, we realized, well, you can really use a tunable for anything. Okay, and increasingly people conceive of it as a way of the programmer defining the search space. Now, given this assumption, if a programmer is aware of this assumption, they probably aren't going to pick things to be tunables that are going to make the search space very jagged. You're going to hand off the things that you think are going to be relatively smooth, and you'll probably play with the set of tunables to see. If you suddenly make something a tunable and the performance gets much worse, well, maybe that was something that was too hard for our current search algorithms to figure out. But your point is well taken. We may eventually have to abandon this particular search strategy and do something more sophisticated if we want to support arbitrary things as tunables. Yeah. Okay, now performance results. So let me show you, and I'm just going to walk through some performance results on different kinds of machines and make some comments about what works well and what doesn't work so well. So here's a set of essentially scientific applications. So the very basic, simple things like dot product and things like that, two-dimensional convolution, a 3D FFT, and then the two bigger ones, gravity simulation and in-body problem, and a fuzzy protein string matching algorithm. So these two are actually fairly complicated. They have multiple different tasks and multiple calls, and fairly complicated control flow in that a given task will have several different subtasks that it calls. All right, and then in each case we use the best available implementation as the leaf task, as the sequential leaf task. And in some cases that was vendor supplied libraries, and in other cases that was a graduate student sitting and sweating for a weekend learning how to use vector intrinsics on some obscure machine. But we basically tried to get something that was reasonably fast because if you're going to compare to the you get artificially good results if your leaf tasks are too slow, intrinsically slow. And so here are some of the machines we run on, and I guess the thing I'm most proud of, or one of the things I'm proud of in this project, is how many different kinds of hardware we run on. We actually publish on lots of different machines without without too much difficulty. So here's a just a standard Intel machine, a scalar. We call this scalar. It's just a standard sequential processor, 8-way. Excuse me, an 8-way shared memory machine. Disk is a Intel P4 attached to a disk. So this is for doing out-of-core algorithms where the disk is treated as another level of memory hierarchy. And I should say that file operations are used as the communication protocol. So you use the file system to move data back and forth. A cluster, the cell processor, and then a PS3, which is a couple of cells inside of a Sony PlayStation. So here's what the results look like for all of the applications on all of these single or two-level machines. Okay, and this is the green bars here. Green means this is time we're spending in leaf task execution. Red means time spent. Red means time spent in the overhead of the Sequoia runtime, and gray here is communication. So that's time spent moving data around in the machine. Okay, and the important thing, I guess there's two lessons here. First of all, there's not a lot of red. All right, so we have one thing here which I think was due to a bug, but other than that, we're doing pretty well in keeping the amount of red stuff pretty small, so we're not spending a lot of time just in system overhead. The other thing is that there's no magic. I mean, the fact that you can write hierarchical programs doesn't mean that they're not going to be communication bound. Okay, so here, we have some architectures here where it's just like doing an inner product from disk is just ridiculously slow. I mean, you're reading in these vectors from disk, and then you're doing an extremely small amount of computation, and then writing back one word. All right, so it's going to be slow, and it's going to be communication bound, and that's just the nature of the problem on that particular architecture. But some other applications have enough compute to computation ratio that even with a very unbalanced machine where the higher levels are very, very slow compared to the leaves, you're still able to keep the leaves quite busy, okay, because the kernel involves a lot of compute for the amount of data that's moved. So another way of looking at these, understanding these numbers are we making maximum use of the resources? So we have essentially two resources, compute and communication. And one way to decide whether the Sequoia compiler is doing a good job is, are we maxing out at least one of those? So are we either bandwidth bound, meaning we're really using all the bandwidth in the machine to move as much data as possible, or are we compute bound? Okay, you can see in all of these systems, the scheduling that came out, we managed to max out one of the resources. And so you can't do any better than that. I mean, if you're using the entire resource, there's nothing you could do to make it faster. Yeah.
So bandwidth bound doesn't necessarily mean your compiler's doing a good job. You could be doing a lot of unnecessary.
Yeah, even as I was saying that, I realized I didn't put it quite right, and you're absolutely, and thank you for correcting me on that. So it could be that there's a tremendous amount of unnecessary, it's true. There could be a lot of unnecessary copies going on in here, and it would still max out the bandwidth, right? So what you can see from here is that it's not sitting around doing something else like runtime overhead, where it's neither using the network nor using the compute. Okay. Now we can also look in the code and see if there are extra copies left in there, and there aren't. Okay. In this case, for these, these are simple enough applications that we can actually see that the copy elimination worked well. All right. But it also doesn't mean, for example, that you couldn't write the algorithm a different way and have a more efficient use of the resources. So you're absolutely right. Okay. So I have to qualify the statement a bit. Yeah.
What is 100% compute utilization?
What is it?
Yeah. How do you define?
I mean that you're computing in the task. You're doing task work that percentage of the time. So you're not in the runtime system. You're in the task at that level doing compute all the time.
This might go back to the previous question. If you're hitting 20% cache hit ratios, is that considered 100% utilization?
That would be considered 100% utilization in the case that we did that. But remember, we also, for cache-based machines, we will block for the cache. Okay, so if you're blocking in the, if you're in the L, so you look at the leaf level and you see if you're hitting, you can see if you're hitting, in that, you're sized for the cache, and so if you see 100% utilization, you imagine that you're doing pretty well.
So I guess the question I intended to ask was,
yeah,
you're calling, I suspect,
Right.
And then you've got your upper level glue that sort of
Yeah.
glues together these things.
Mhm.
How much efficiency do you lose in that upper level glue versus?
Yeah, so that's the red bars here. Okay, so where we're spending time in the Sequoia runtime system is the red bars. Now, this is only for a two-level system. Okay, yeah.
So
Nope.
in SGMM, you would probably, this is optimized for L1 and L2 and some very exotic, whatever the vendor supply class would do.
Yeah.
Where does that overhead? Now you're not hitting 97, 98% hit ratios. You're not hitting 95% hit ratios. The loss in performance going from 97 to 95% hit ratios while you're actually doing.
Yeah. Okay. So I think maybe I can answer this question with my next slide. All right. Actually, give me just a couple of slides because I also have absolute numbers and comparisons with best known. All right. All right. So then ask me again. Okay. So here are the gigaflop numbers for each of these applications on each of these machines. So these are the absolute. This is the absolute performance. Okay, and you can see there's a wide variety, orders of magnitude difference in the absolute performance. So I'll pick out a couple of numbers here. So on the cluster, Intel's number for the was 101 gigaflops, and we come in at 91 gigaflops. Okay, so we're about 10% below what Intel is able to achieve. And then on the SMP, we're actually slightly faster, okay, with the same code. All right. Okay. On the cell, we actually, at the time we did this, we were the best. Hold on a second here. We were, what am I trying to say? Yeah, we were the best, or close to the best, FFT. Okay, so we were at 54 gigaflops. Mercury Computer had a proprietary implementation at 58, and the open source FFTW at that time was at 35. Now, they probably improved that since then, okay, because it takes a while for them to get their performance up. But we were competitive with the best known implementations. We were slightly faster on the cluster than the best implementation at the time, and we were a little below FFTW on the SMP, okay, but still in the ballpark. Now, these other two applications, the best known implementations of these look like had these kinds of numbers, and we were doing a little bit better on Hammer, and on Gravity we were actually getting quite a bit more. Okay, 4 billion, 3 billion. All right, so these are different ways of understanding the performance. Okay, so I guess there's at least 3 different ways of understanding the performance. How much runtime overhead is there? How much time are we spending in our system? That's not useful work or communication. How well are we utilizing the resources? And then absolute, how do we compare to best hand-coded versions? And so these are just some data points that suggest that we're not doing terribly. Okay, that this compiler is actually able, with this strategy, you're actually able to write programs that actually will perform reasonably well. Okay. So maybe my favorite one is putting a disk is disk attached to a processor or doing out-of-core algorithms. So here, some interesting things to point out is that some of the algorithms. So you actually can see that in some cases the the scalar version versus doing everything from disk. You can see horrendous slowdowns here because there's not very much compute to computation, but some applications actually this is okay. So just for a simple implementation of an out-of-core algorithm, if you want to suddenly do a much bigger problem size and your problem has enough computational intensity, you can just say add another level, attach a disk, and you can suddenly just do a much bigger problem without having to write your own out-of-core implementation. All right? It will take care of moving the data to and from disk for you. Here's the cluster of Intel machines versus the PS3. Okay, and you can see that we're actually pretty competitive for some applications here. The cluster was a $150,000 machine, and the PS3 was $500. All right. And so now the PS3 might not be your favorite compute platform. It's a funny form factor for one thing. But it does point out, I mean, this is what's driving everybody to switch over, switching high-performance computing to GPUs. All right, because it's so much cheaper. Then it's not even that you get higher performance, it's that you get much higher performance per dollar spent. And these kinds of ratios explain all the rush into GPU computing these days. All right, so that's 2 levels. Okay, so part of the motivation was to go to multi-level machines, all right, with more than 2 levels. So let me show you a few results there. So we'll talk about a cluster of SMPs, a disk plus a PS3. So a PS3, remember, has 2 cell blades in it, and then we attach a disk to it to do out-of-core stuff. And then a cluster of PS3s. All right, so here are the runtime utilization numbers. And you can see that on the compute-intensive ones, we're doing quite well in terms of the red. There's 2 different colors here for overhead. Okay, so there's the brown for between the root and the first level, and then there's the red for the intermediate level to the leaf. Okay, and then there's 2 different colors for transfers, because there's 2 levels of communication. And then the green is leaf task execution again. All right, so you can see some, you can see this one here. All right, so this was definitely due to a bug, which I believe has since been fixed. But and you can see there's more overhead than in the 1-level system. But again, if you have enough computational intensity, of course, the overheads are not going to be bad. And even for some of the less intense ones, but still, we're doing pretty well. Okay, for the least intense ones and the multi-level ones, we have some inefficiencies we have to get out of the system. So here's an SMP versus a cluster of SMPs. Okay, so on the cluster, you can see that in some cases, like FFT, actually performs somewhat worse than just on a simple SMP. All right, but in some other cases, we get similar or slightly better performance. Okay. So I should say here's the same total number of processors, all right? And not surprisingly, the compute-limited applications don't care about the interconnect. They don't care about what's holding them together because they've got so much computation to do. You do see a bump, though, in the compute-limited ones, I'll just say, because we do it multi-level and we do divide and conquer. I mean, you are getting some advantage from increased locality on the SMP. You get the problem down onto the SMP, and then it stays there. All right, and so we get a little bit of a bump there. All right. The disk plus PS3 comparison. So here's just with a PS3, and as you can see, in some cases, the slowdowns are just amazing. But some applications actually have enough computational intensity to run from disk to do out-of-core stuff without significant slowdown. But in other cases, we just can't move enough data because the cell has a very small local memory, and you just can't. It's too inefficient to transfer that size memory from disk. It doesn't not enough to support, and it's too slow. So it's just not enough to support utilization of the machine. So this is a very unbalanced machine. Okay, so as I said before, there's no magic. You can build these machines, we can compile for them, we'll run on them, but the application might not work very well just because of the ratios of if it's not well suited to that particular configuration. All right, and then we talked a little bit about the PS3 as a compute platform. But now I should skip ahead because we're running out of time. So here's a little bit on the AutoTuner, and I don't know if you can see the black numbers, but I'll just tell you the yellow numbers are better than the black numbers. And this is just to show that the AutoTuner actually improves our best hand-tuned version. And we actually did spend a significant amount of time hand-tuning these because we wanted to publish these numbers. All right. Okay, so the summary is that deep memory hierarchies pose a programming problem. It's our thesis that you need to make this explicit. Programmers need to understand the cost of their memory accesses, and you need some way for programmers to talk about locality in their language, and not just at one level. And by having this hierarchical model, which is relatively abstract, we're able to actually allow programmers some control over locality and still be very portable. All right, and that's the tension that we wanted to resolve. So in the approach, of course, is to express computations as hierarchies of tasks. All right, so I think I will stop there. And if there are more questions, I'd be happy to take them.